Alright, so in this video we're going to dig into more of the underlying math of waves and the richness of that. This is what you're going to be getting into more in first and second university in physics, especially if you continue through in a major. It's really exciting, really beautiful. It's definitely beyond the scope of our course, so this is an optional video. I think it's really fun and interesting, so you are welcome to watch it if you're also interested in this sort of thing. Alright, so the math of a wave. I'm going to just show you a wave function first, and then we're going to look at why does this make any sense. First, it kind of makes sense that it's a sine function. Could have been a cos function. That's actually just standardizedly picked sine functions. So it's got some amplitude A, and then it's got all this interesting stuff in here. The first thing that I want you to notice is there's actually two variables here. There's position x, and there's time t. And there's also two positions. So this wave is telling you all about y. And y is the vertical height of, say it's a wave on a rope, it's the vertical height of the rope above equilibrium. Maybe it's a water wave, then it's the height of the water above equilibrium. That actually doesn't matter depending on the type of wave. So here's equilibrium, right here. Y is going to be the height above that equilibrium point. So my wave goes up and down and so on, up and down forever, right? Y is how far am I above equilibrium, or how far am I below equilibrium at any point in position and in time. So this is a bit of a weird function for you. I don't know that you've met a function before that depends on actually two variables. When you get to university, if you take anything mathy, you'll get really great at doing functions of 2 and 3 and 4 and 5 variables. Not 5 that often, but 4 is really normal. Here, your two variables are horizontal position and time. So time, that's t, and horizontal position, which is x. So that kind of makes sense, right? As you change horizontal position, if I make this axis x, here, then the wave will be going up and down with x, right? But I could have also made this axis time, because waves, even if I look at a single point on the wave, it's actually changing with time. The rope is going up and down, it's moving. So this depends on two things, both horizontal position and time. Amplitude, a little more straightforward. So that's just what is the highest y I get to. So it's the highest point my rope reaches above equilibrium. K looks new, but it's not. It's actually just related to the wavelength. K's name is the wave number. It's just 2 pi divided by the wavelength. X, of course, is your horizontal position of the rope. Omega, also not W, by the way. A lot of people get this mixed up. W is like this. Omega is like this. Omega is a Greek letter, and omega is angular frequency. And it's 2 pi times the regular frequency that we've been talking about in class. It's also because frequency is 1 over the period, right? So that means that omega will also be 2 pi divided by the period. That's another way that we could describe omega. And little t is the time, just how much time has passed. Alright, so let's try and make sense of this equation. Like, why is a right traveling wave, why does it have a negative sign there, and a left traveling wave has a positive sign there, and everything else about them is the same? And why is it even set up this way with a kx plus omega t or a kx minus omega t? It kind of looks strange. So to understand it a little bit better, we're going to sort of simplify things. Our first simplification is we're going to imagine we're at a certain moment in time. So we're going to pick time is equal to 0 because that's an easy moment in time to do. That's like taking a photo of your wave. So imagine you've got this wave on a rope, up and down, up and down, up and down, and it's moving, maybe it's moving to the right. We're going to take a photo of it, like snapshot right now. It's just going to stop moving. And that way we can at least look at, does it look the way it's supposed to? Does it go up and down? Is the wavelength of the wave that we take a photo of actually lambda, like it should be, right? But it's pretty hard to see with this equation here. So that's what we're going to do. We're going to say t is equal to 0. That means our function y is going to simplify to just a function of x, and it's going to be a sine of k. I'm going to rewrite k as 2 pi over lambda times x, and then minus omega times t, and t is just 0. So I've chosen this moment in time of 0. That kills that second term, right? That whole thing is 0. And that makes my equation simpler. So y is just a function of x, and its amplitude times sine of 2 pi over lambda times x. Okay, does this function make any sense? Let's just look at a few points. So I'm going to look at a few x's, see what the y's are, see what the height of the wave is, to see if this makes sense. Let's start with x is equal to 0. In that case, y is going to be a times sine of 2 pi over lambda times 0. That's all 0 inside there, right? Sine of 0 is 0 times a is 0. So that's going to give me a y of 0. And I'll just plot that over here. So here I'm plotting y just as a function of x, not time right now because I've picked time to be 0. So at 0, y is 0. That fits what I should see in my snapshot, right? If my wave starts out here, there's y and x or t, it should start out at 0 and then do a sine function from there. The next point that I'm going to look at is 1/4 of lambda. So this one looks a little bit messier, but y is going to be a times sine of 2 pi over lambda times a quarter lambda is like lambda, oh, I put a 4 on the bottom, sorry, lambda on the bottom, lambda over 4, that's what I meant there. The lambdas cancel, right? And that gives me 2 pi over 4, or half of pi. Sine of half of pi, or sine of pi by 2, is 1. So that's going to be just 1 times a, which is a. So that actually tells me that at sine of pi by 2, I reach the amplitude, which I should. So this is a quarter lambda here, and I reach a, the amplitude. That makes a lot of sense. My next point is going to be half of lambda. I'll get y is a sine of 2 pi over lambda times lambda over 2, half of lambda. The lambdas cancel, the 2's cancel, I get just sine of pi. Sine of pi is equal to 0, so I get a 0 here. So at half of lambda, my function goes down to 0. Keep going here, at 3/4 lambda here, I'll let you work that one out, where you're going to get y is equal to negative a. And our last one, so that would be down here, right there. Our very last one is when x goes all the way to the wavelength, I get back to y is equal to 0. So I get a node there. If I sketch this out, I get a beautiful sine function, and this is lambda, this is 3/4 of lambda. What I noticed that's important here is that the wavelength of this function, right, that is one full wavelength, and it ends at lambda, which makes a lot of sense because lambda is the wavelength of my wave. All this is telling me is that this equation, which looks kind of crazy, if we choose a snapshot in time and simplify it, what we see is just a regular old sine function with a wavelength of lambda, which is the wavelength, that's by definition wavelength. So it's working like it should. Okay, now let's try and understand whether this right traveling, left traveling thing makes any sense. Okay, so let's look at a wave. Just draw myself out a wave. Here it is. And here's equilibrium through the middle here. And I'm going to draw my y-axis here, because then right after y I see that normal sine function that I'm expecting, right? So that's a good point to start. But also it's important because if I have a right traveling wave, what you should notice is that as this wave moves forward, it's actually going to start out by going down, right? This is going to be what sort of plays out. This is really tricky. I wish I could like animate my paper. But as this whole thing slides this way, this piece here is going to be passing by that 0 point. So this is x equals 0 here, right? So at x equals 0, our rope is going to go down first as this piece goes by, and then when this piece reaches, it's going to go up to 0, and then as this piece goes by, it's going to go up and down, and it'll just keep going up and down forever, right? That's what should happen if this wave is behaving like a normal wave. Picture it like a person just bobbing on the water. So the wave is going by. If the person is located at x equals 0, they're going to go down first and then up and then down and then up and then down and then up, just bobbing on the water there. let's see if that actually works out here. So we're going to pick x equals 0. It's a nice simple position. Then y is becoming just a function of time. And it'll be a sine of x k times x is 0 minus omega t. That whole term is gone because it's multiplied by 0, the k there. So I get just a sine negative omega t. You may know this about sine functions already. If there's a negative sign out in here, you can actually just bring it out front. So it'll be negative a sine of, and I'm actually going to replace omega with what it is. And the definition I'm going to use is 2 pi over capital T. The reason why I'm choosing that definition is because it looks an awful lot like what we just did here, sine of 2 pi over lambda times x. What you can see is that this lambda on the bottom here became the wavelength of my wave. That's going to be true here too. The capital T, the period on the bottom, becomes the wavelength or the length of the wave in time. So it's not the wavelength. The wavelength is a unit of meters. It's a distance, but it's the length of the wave in time when time is our axis that we're looking at. Which is exactly what we should expect. The period, the time it takes to get back to where the wave started is what we should be seeing here as the length of the wave. The other thing you should notice is this negative sign is actually important. For a right traveling wave, we're expecting the person to bob down first, right? So that means that negative sign makes that happen for us. If I sketch this wave, it's going to look like this. It'll be y and time here. Because of the negative sign, it flips the function upside down. So if you remember from your grade 11 functions course, negative signs out front just make the function like flipped upside down, flipped on the time axis or flipped on whatever horizontal axis you have here. It's going to look like this. Instead of this sine function here with x, which went up first and then down like a normal sine function, this guy is going to go down first and then up. And the length of that wave is going to be the period. That should end up as being the period here, which is exactly what we would expect for a right traveling wave. And so that's why the negative sign is essential for a right traveling wave. If that was a positive sign, that would mean the wave is moving the other way. That would mean that you should be going up first, which if you imagine this wave moving this way, that's exactly what you would see. So that's why the positive sign is for a left traveling wave. Okay, that's traveling waves. Let's dive into standing waves. So if you remember when we talked about standing waves, in class we used some animations to show that a right traveling wave plus a left traveling wave makes this standing wave, this wave that appears to not travel at all. But we did no math behind that. We just sort of looked at it and said, oh, it kind of looks like that. There are actually some really beautiful math behind it. To add two waves together, you literally just have to add them. So this is the equation for a right traveling wave, right? Here's the equation for a left traveling wave. If we want to know the equation for a standing wave, I'll call it maybe capital Y because it's standing, it's more important. That's going to be just my right traveling wave, which is a sine of kx minus omega t, plus my left traveling wave, which is just a sine of kx plus omega t. That's actually all there is to it, sort of. The problem is that this equation looks like a mess. Like, how can you tell that this is a standing wave? It doesn't even look like a wave. It looks like two added sine functions. Who knows what that looks like? So clearly it needs to be simplified. This is where a little bit of advanced functions from grade 12 comes in. If you've taken it already, then you're in luck. If you haven't taken it, then this is your chance to get a little bit ahead, perhaps. We can actually use two trig identities. So you've seen trig identities a little bit in grade 11 math, or you will see them if you're currently in grade 11 math or taking it next semester. It's a trig identity is just a way to simplify a trig function. We use them for proofs and things like that in math a lot. In physics, we use them for making things simpler, making them make sense or fit into other places. So that's what we're going to use them for here. So these are two trig identities. They're really useful ones because they're for sine functions that have things that are added together or subtracted inside. And that's exactly the problem we have here. Sine functions with stuff added and subtracted inside. Okay, so our first one, this is going to get really big and then it'll get small in a minute. So here's our standing wave, big Y, is equal to A times, oh my goodness, okay. I'm going to put big brackets here. Sine of kx minus omega t. So I'm going to use this second trig identity first. So the kx, that's like the a here, minus b, which is the omega t. So when I use this trig identity, everywhere I see A, I'm going to be putting in kx. Everywhere I see B, I'm going to be putting in omega t. All right. So that I'm just working on the first part right now. We're going to do the second part in a second. It'll take a little bit here. So sine of kx minus omega t becomes sine of the A, which is kx, times cos of the B, which is the omega t, minus cos of the A, that's the kx, times sine of the B, that's the omega t. And that is just the first part. Next I have to do this one. So that's all plus A times this guy. So this is going to be the other trig identity. It's a sine of A plus B. And again, A is the kx and B is the omega t. So sine of A, I put in the kx for A, times cos of B, I put in the omega t for B, plus cos of A, I'm going to put in the kx for A, sine of B, which is the omega t. Whew. Feels like a mess. It will simplify very, very quickly. First thing we can do is just multiply the a's into those brackets. That seems like an easy move. So I'll get A sine of kx cos of omega t minus A cos of kx sine of omega t plus A sine of kx cos of omega t plus A cos of kx sine of omega t. It looks awful, but it's actually going to simplify really, really quickly. Because what do you notice here? Here I've got a negative A cos of kx sine of omega t. Here I have a positive A cos of kx sine of omega t. Those terms are identical, except for one is positive, one is negative. They're going to cancel each other out. That's gone. The other great thing I have is an A sine of kx cos omega t plus another A sine of kx cos omega t. What I have here is two of these A sine kx cos omega t's. So altogether, y is just 2 of this bit, the A sine kx cos omega t. And that is actually the equation of a standing wave. Right there. It looks a lot simpler, than this crazy mess that we started with in just like one line with our handy trig identities. That's what I love about trig identities. But does it actually make sense? You can tell that maybe it looks a little more trig functiony. At least we've got rid of all their pluses and minuses everywhere that were messing it up before. Let's look at it a little bit closer. So for it to be a standing wave, there have to be some points that are nodes. There have to be some points that are 0 no matter what the time is. So that was not obvious at all in this place where we started here, that for certain x values, this y function would be 0 no matter what time was at all. That's definitely not clear here. But hopefully with the simplified version, it can become a little bit more clear. So nodes are places where if x is equal to some value, y will always be 0 no matter what happens for time. Is that true? What I'm looking for then in my equation, y as a function of x and t, is 2a sine of kx cos of omega t. I'm looking for the points where this is 0. And if that term is 0, then the entire thing is going to be 0. And you could put in time as anything at all. It won't matter. That whole thing will always be 0. Y will always be 0. And because this is actually a sine function, sine functions regularly go to 0. They go to 0 at, if this is my x here, this is y. A sine function goes to 0 at x equals 0. It will go to 0 at half of the wavelength. It'll go to 0 at a full wavelength. It'll go to 0 at 3/2 of the wavelength, and so on. At those points, you'll always get nodes. So in here, the wave can be vibrating up and down, moving wherever it needs to. It'll do this a second later. That's fine. And then maybe this a little bit later. And this a little bit later than that. But at these points here, even as time lets the wave move up and down, those points are always nodes. that perfectly fits what a standing wave should look like. And in fact, that is the equation of a standing wave.